Hello. All participants are requested to stay connected. The guests are coming soon.
ऑनलाइन मोड में
ऑनलाइन
Hello. Participants are requested to stay connected. The session will starting within 5 minutes.
हॅलो विकार सर.
हा सर, आवाज येतो माझा?
हो येतोय आवाज सर.
ओके, स्टार्ट करायचं मग.
सर मी एक इंट्रो देतो तुमचा, त्याच्यानंतर स्टार्ट करू.
माझा आवाज क्लिअर येतो का सर?
येस सर, येतोय आवाज.
ओके ओके.
ओके. Very good evening to all present here. It is my pleasure to introduce our distinguished speaker for today's session, Dr. Ashish D. Vikhar, a highly experienced academician and author in mechanical engineering. Sir has more than 25 years of teaching experience. Dr. Vikhar sir is recently working as senior lecturer in the mechanical engineering department at Government Polytechnic, Pune. Earlier, he served as senior lecturer at Government Polytechnic, Jalgaon, and has also worked as associate professor and assistant professor at SGD College of Engineering, Jalgaon, and at SSBT's College of Engineering and Technology, Bamburi, Jalgaon. He holds a PhD in mechanical engineering, ME in mechanical engineering, B in production engineering, and ADCSSAA qualifications. Dr. Vikhar has published many research papers in Scopus conferences, Scopus indexed international and national journals, conferences, and seminars, and has authored several books, including Engineering Thermodynamics, Thermal Engineering, Strength of Materials, Renewable Energy Technology, Fluid Mechanics and Machineries, CAD/CAM, Solid Modeling and Drafting, and Engineering Graphics. Alongside his academic contributions, Dr. Vikhar is also a professional cartoonist, with his work appearing daily in various newspapers and magazines. With his rich blend of teaching experience, publications, and creativity, Dr. Ashish Vikhar sir is well placed to guide us in today's session. So, on behalf of our institute, I request all the participants kindly join me in extending a very warm welcome to Dr. Ashish Vikhar sir. Welcome you, sir.
Thank you so much, sir.
Yes.
Can I share the screen now?
Yes, sir. Yes.
On the share button, I am going to click, and this PPT. Okay. So in this way, I am going to present the session.
Okay. Sir.
Hello, everyone. I am Dr. A.D. Vikhar, and I am the faculty in Mechanical Engineering Department at Government Polytechnic, Pune. In this 1 week AICTE-ATAL-FDP on role of robotics and mechatronics in industry, I am going to present my topic, robot communication protocol. Robot communication protocol is another important topic which is highly important in robotics and automation. As we all know that since 15 September 2025, this ATAL-FDP has
Sorry
been...
to interrupt you, sir. Can you make it full screen?
Yes, sir. Yes, sir.
Yeah. Thank you.
Yes, sir. Wait a minute, sir. Okay. Is it now visible, sir? Full screen?
Yes, sir. Yes, sir. Thank you.
So once again, welcome to this session on robot communication protocol. Till date, we have seen a lot of information regarding some important topics related to it, like what are the recent advancements in robotics and automation. After that, on day one, we have seen that computer-aided CAE. After that, robotic system, as well as robotic programming. Now, today we will go for robot communication protocol. robot to robot protocol. This is nothing but the topic, and in this presentation, I am going to explain following contents. I am going to start with first some examples. After that, I am going to give some introductory concepts related to robotic or robot to robot protocol. Then after that, we will try to know the importance of this robot to robot protocol or robot communication protocol. Some important definitions that I am going to explain. And after that, I am going to come. I am coming to the important topic. What are the types of robot communication protocol? And lastly, we will discuss regarding selection of robot communication protocol methods. What are the criteria? So in this way, these are the contents. In that manner, I am going to explain my session. So let us start with this important example. As we know, the drone. So a fleet of drone might communicate to carry out a search and rescue operation. One drone might spot a target area of interest and automatically alert others to coverage on that location, sharing GPS coordinates through a secure wireless network. So here we are seeing one example in which there is a use of robot communication protocol wireless network. So at the last, you will see that here there is a wireless network. So wireless network is one of the protocol which is used in this drone fleet of drones. So one drone might spot a target area of interest and automatically alert others to coverage on that location. And for that purpose, GPS is used. And for connecting wireless network, this one kind of protocol that has been used here. Second example in which you will see another method, another robotic protocol method that is called ZigBee protocol. So it is an example of robotic cleaning machine in which you will see that, or imagine that a network of robotic cleaning machine in a mall. It is using a ZigBee protocol to communicate with central server. Due to ZigBee protocol, low power requirements, the machines can operate for longer hours without the need for frequent recharges. So this is nothing but the feature of this ZigBee protocol. So what is that? Low power requirement, and the machines can operate for longer hours. So in this example of robotic cleaning machine, we will see the use of ZigBee protocol. This is one of the method or one of the another important tool for connecting with the system of robotics. In the third example, we will see that uh, in the third example, we'll see that and in a military application, securing robot communication. So in that military application, securing robotic communication is paramount and it is having very wide importance. Implementing encryption protocols and intrusion detection system which can safeguard military robots from malicious attacks, ensuring that they can operate effectively. So here in this also we will see that the application of robot communication protocol, encryption protocol or intrusion detection system. So in these three examples, we will see the importance of robot protocol, robot communication protocol. One example of it is fleet of drones that I have explained. After that, robotic cleaning machines, and in military application, how robot communication is possible. So these are some of the examples from that we can have the inclination of importance and the nature of working of robot protocol, robot communication protocol. So let us start with this introduction. In this now today's world, we are using artificial intelligence and machine learning, and robots are increasingly capable of understanding and responding to complex commands. So complex commands are now receiving and exchanging by the robots, and this enables seamless interaction in industries like manufacturing, healthcare, and customer service. So robots are used in these industries of manufacturing, healthcare, and customer service. So robot communication protocol play a very vital role in ensuring data exchange between the robotic components, sensors, and control systems. Robot protocols allows robots to interact efficiently, enabling real-time decision making and automation. So this real-time decision making is very much important during the operation of robots, and this is possible because of robot protocols, robot communication protocols. Without effective communication protocols, robot would struggle to perform coordinated tasks in industrial, healthcare, and consumer application. So there should be the effective communication protocols. In some examples that in the previous slides we have seen, there are three important protocols. But what are the other important protocols that are that we are going to learn, that we are going to study in the next slides. So without effective communication protocol, robot would struggle to perform coordinated tasks in industrial, healthcare, and consumer applications. In the world of robotics, robot communication protocols play a vital role, ensuring seamless data exchange between the robotic components, sensors, and control system. So robotic component in robots, various robotic components are there, sensors are there, and control systems are there. They are connected with the help of robot communication protocols. So robot communication protocols allows robots to interact efficiently, creating real-time decision making and automation. So automation is possible because of robot communication protocols. In this way, these are nothing but some of the introductory concepts related to robot communication protocol. Let us see the importance in short. Robot in environments like warehouses, hospitals, in space missions rely on smooth communication channels for optimal performance. To give the optimal performance, robots are relying on smooth communication channels. This field of robot communication protocol combines concept from engineering, computer science, and robotics with the goal of creating efficient and effective communication system for robots. So this robot communication protocol combines the concept of all engineering, computer science mainly, and after that the robotic science. As a rapidly evolving field, understanding the principles and technologies behind robot communication is essential for those interested in future automation and robotics. So, if you want to know, if you want to go in the field of automation and robotics, then we should understand the principles and technologies behind robot communication. So, this is nothing but the importance. Then we will come to know the what are the important definitions in this robot communication protocol. There are three important definition. Number one is what is protocol, what is communication, and what is communication protocol. So protocol is a set of rules and regulations, and that we set for better communication between the robots and its components. Communication means exchange of information from one robot system to another robot system with a medium, that is called communication. And our communication protocol means again a set of rules and regulations that allows two robotic devices or more robotic devices to connect the exchange or uh, to exchange the data with one and another. So data exchange is nothing but communication protocol. So in this way, from this important three definitions, we come to know the important concept that how this communication protocol is important. Communication protocol device or its rules are helping to exchange the data from one robot to another robot. Robot communication protocol is also called as a field bus. Therefore, field bus also describes the set of rules to be used in communication between robotic devices. So handshaking, if you see the handshaking of the robots, then handshaking also of the two robots refer to a way of two robots of which they initiate the communication. So handshaking is a basic fundamental. Many times two robots that we see the handshaking. So this is nothing but a communication. So robot communication involves the exchange of information between robots or between the robots and humans using various methods. Some examples that I have mentioned here. Number one is wireless network, sensors, and speech recognition system. So wireless network, how they work, sensors, everyone knows there are different kinds of sensors that are used in robots and other kind of machine. Speech recognition, on the basis of that also communication is possible. Now, types of robot communication protocols. This is nothing but my topic. And in this, there is a categorization. Number one is wired communication protocols. Number two is wireless communication protocol. Number three is real-time communication protocol. Then Internet of Things and cloud-based communication protocols. Some other methods of robot communication are infrared communication, ultrasonic communication, visible light communication. That's three important communication that I am going to cover. Other also are mentioned, but that I have not covered in this. So here there are four types of mainly robot communication protocol. First, starting with wired communication, then wireless communication, then real-time communication, then IoT and cloud-based communication. And other types include infrared communication, ultrasonic communication, and lastly, visible light communication. So these are some of the other methods. So let us start with wired communication protocol. Wired means there is a physical contact with the help of wire. So this is a most important, most traditional method of robot communication, and it involves connecting robots with physical cables. Wired communication is reliable and robust. So it can be a limiting. Limiting means it has having some limitations because we cannot extend the wire. So it can be a limiting, as robots can only communicate with each other if they are physically connected. So with the help of wired communication, uh, robot are physically going to be connected. Physical cables such as Ethernet cable, RS-232 cable, and CAN bus cable connect robots directly to each other. These cables provide a reliable and robust connection for data transmission. So this is one of the reliable way of communication between the robot, that is a wired communication. Sensors such as proximity and touch sensors can detect the presence or contact of other robots, enabling them to communicate and coordinate their actions. So proximity and touch sensors can detect the presence or contact of other robots with the help of this wired communication protocols or wired communication method like Ethernet cable, RS-232 cable, and CAN bus cables. So what is this Ethernet or IP? A high-speed protocol used for industrial automation, offering low latency and robust data handling. So this is one of the method of wired communication protocol, that is Ethernet. Second one is control area network. Under the wired communication protocol, second method that we can use is control area network, like WAN, LAN, but that is not has been used, but can be used. Control area network commonly used in automotive and industrial robotics, and can enables efficient data exchange between multiple microcontrollers without a host computer. So this is nothing but the important point related to the control area network. As I have mentioned, RS-232 and RS-485. These serial communication protocols are used in industrial robots for real-time data transfer. RS-485 supports multiple devices on single network, making it more scalable than RS-232. So these are two important wired communication protocol. One is RS-232 and RS-485. But RS-485 supports multiple devices on a single network. Modbus. This is another important wired communication protocol. Modbus, a simple and reliable protocol used in automation system for communication between programmable logic controller. We know what is programmable logic controllers, and in that Modbus is used as a wired communication protocol. In robots also, this can be used as a wired communication protocol, Modbus. So Ethernet, CAN, RS-232, RS-485, Modbus, these are on your screen, which are nothing but called as a wired communication protocols. Let us come to know about next important one, wireless communication protocol. Wireless, as we know, there is no use of physical cable or physical wire. This method of communication is important because it allows robots to communicate with each other without the need for physical cables. So physical cables that are not going to use, and wireless communication can be used over various frequencies, including radio waves, Wi-Fi, and Bluetooth. There is a far use of Wi-Fi and Bluetooth, and with the help of Wi-Fi and Bluetooth, this wireless communication protocol is possible. Radio waves are used for long-range communication between the robots, especially in outdoor environments where wired communication is impracticable. So radio waves are radio waves can be used in this manner. So radio waves are used for long-range communication between the robots. So first, Wi-Fi wireless fidelity. So this is nothing but first wireless communication protocol, Wi-Fi. Okay. So Wi-Fi network allows robots to communicate wirelessly over short distances, enabling them to share information and collaborate within a confined area. Everyone knows what is Wi-Fi, and they are also very popular in using in robotic communication. So Wi-Fi allows robots to communicate wirelessly over short distances. So here short distance is important criteria, enabling to share information and collaborative within a confined area. So within a confined area, we can use a Wi-Fi. So Wi-Fi network used in autonomous robots and IoT connected devices. Wi-Fi allows remote operation and real-time data transfer. So real-time data transfer is the important feature of Wi-Fi network. What are the applications? In this, Wi-Fi is used in industrial robots and primarily used in automation of various automatic devices used at home and offices. Home and office automation also. Let us see what are the advantages of Wi-Fi communication protocol. Wi-Fi antennas offer a relatively high data rate, allowing robots to transmit large amount of data, including high definition videos. Second advantage is they are also ubiquitous in many environments, make them convenient for robot integration. So in this way, these are the two important advantages we get from the Wi-Fi or wireless fidelity. One is Wi-Fi antennas offer relatively high data transfer. As we know, sharing information and collaboration with robot to robot is important, and the data transfer is at the high rate with the help of Wi-Fi, allowing robot to transmit large amount of data. Okay, so this is nothing but the important advantage. So they are also uh, integrate all kind. In this way, they can integrate the robot system. Second important method under wireless communication is Bluetooth. So Bluetooth is a short-range wireless technology suitable for communication between nearby robots, and such robots working on the same assembly line. Same assembly line. If the robots are working on the same assembly line, then in that case we can use a robots. In that case, we can use a Bluetooth. So Bluetooth is ideal for short-range communication. So that's why it is called Bluetooth Low Energy, BLE. So Bluetooth is ideal for short range communication. Bluetooth is often used in consumer robots and wearable robots. What are the applications? Bluetooth that we know everyone nowadays. It is used in personal and toy robots and some medical devices. What are the advantages that we get from this type of communication protocol? Bluetooth antennas provide a secure short range communication channel. So it is nothing but a short range communication channel. Bluetooth low energy efficient variant is excellent for devices that need long battery lives but don't require continuous data transfer. So if you do not need continuous data transfer, then we should use a Bluetooth low energy communication method or communication protocol. So in this way, Bluetooth is used in wireless communication protocol. One of the limitations that found with Bluetooth is it has limited data transfer range and range when compared to the Wi-Fi. So Wi-Fi is having more data transfer range rate, while the Bluetooth is having a low data transfer rate. So in this way, this is one of the important limitation that we have with the Bluetooth. Next popular protocol is Zigbee or Z-Wave protocol. So Zigbee is a wireless technology standard used to create low cost, low power, and secular wireless network for Internet of Things devices used in swarm robotics and home automation. So swarm robotics, you might be knowing, but in that area, Zigbee is used. It is nothing but a wireless technology standard used to create low cost. Important is low cost, low power, and secure wireless network. For in this way, this is nothing but the concept of Zigbee. We'll find this application in smart home application, including home automation robots. In home automation robots, Zigbee is used. In this figure, you will see the different applications of Zigbee. So, in smart building, Amazon, Echo, smart watch, temperature monitoring, smart refrigerator, wall control, all these are possible with the help of this Zigbee communication protocol. It is having some much more advantage because they are low power, short to medium range protocols. They can form mesh networks where devices rely signals extending effective communication range. So in this way, this is nothing but the advantage. These are low cost, low power, and secular wireless network. One of the limitation with Zigbee is Zigbee has low data transfer rate or data rates compared to the Wi-Fi. Again, Wi-Fi is better than Bluetooth and Zigbee. So Zigbee is having a low data transfer rate. So this is the Zigbee. Previously, we have seen Bluetooth and Wi-Fi. Now this is nothing but the Zigbee. Next is LoRaWAN. So low range WAN, an acronym for long range WAN area wide area network. So it is a LoRaWAN, means long range wide area network. Is a wireless networking protocol for the Internet of Things, enabling battery operated devices to connect to the internet over a long distances with a low power consumption. So it is a battery operated devices, LoRaWAN. These are battery operated devices and these are used to connect internet over a long distance with a low power consumption. So this is another method or another communication protocol that is called LoRaWAN. It operates in unlicensed radio bands, uses a star network topology and provides end-to-end security. So in this way, it is going to operate in unlicensed radio bands, and the topology which is nothing but used in LoRaWAN is star network, and it provides end-to-end security. So in this way, this is nothing but in short the information about another protocol which is called LoRaWAN or long range protocol, communication protocol. LoRaWAN designed for low power, long range communication, making it suitable for agricultural and environmental monitoring robots. So if you focusing on robots, then agricultural and environmental monitoring robots are using LoRaWAN protocol system. So particularly it is designed for low power, long range communication and mostly suitable for agricultural and environmental monitoring robots. So what is the application? Another, it is used in outdoor applications such as industrial agriculture, as I have mentioned, with robots and drones also that operate over vast areas. In drones also, we can use a LoRaWAN. Let us see what are the advantages. As the name suggests, LoRa offers extended range up to several kilometers and is incredibly energy efficient, making ideal for applications that require data transfer over long distance. So if you want to transfer a data over a long distance, then we can use LoRaWAN, this communication protocol. So it is having one kind of limitation also. It has low data transfer rate than again Wi-Fi. So you see that Wi-Fi is better than LoRaWAN. So LoRaWAN, in the previous slide, we have seen another some of the wireless technologies or wireless communication protocols also. Now this is nothing but a LoRaWAN. Now, third category of robot protocol, robot communication protocol is real-time robot communication protocol. Real-time robot communication protocol. Real-time robot communication protocol are specialized rules. These are specialized rules for transmitting data quickly and reliably between a robot and external systems to enable precise and synchronized operations. So if you want to do synchronized operations and uh, if you want to transmit a data quickly and reliably between a robot and the external system, then we can use these real-time robot communication protocols. So there are three important real-time protocols, real-time robot protocols. One is called robot operating system, like computer is there. In robots, we need a robot operating system. So this ROS, robot operating system communication, it uses ROS framework for handling real-time messaging between the robot components. Second one is Ethernet for control automation technology. This is the second important real-time protocol. Ethernet CAT. Ethernet CAT for control automation technology, which provides real-time Ethernet-based communication. It is widely used in robotic arms and industrial automation. So in robotic arms and in industrial automation, this Ethernet for control automation technology can be used. Third one is nothing but Profinet. Profinet, a protocol designed for real-time industrial automation with high-speed data exchange capabilities. So Profinet is nothing but having one important feature. It is having high-speed data exchange capability. So under the head of real-time robot communication protocol, there are three important methods available. One is robot operating system, that is called ROS communication system. Second one is Ethernet CAT, or Ethernet for control automation technology. And third one is Profinet. So these are the three important methods under real-time robot communication protocols. Now this fourth one is IoT, Internet of Things, and cloud-based communication protocols. So we all know the importance of Internet of Things in this today's scientific and engineered world. So IoT is a network of physical devices embedded with sensors and software to collect and exchange data. In short, this is nothing but IoT. And cloud-based communication protocols are rules enabling these devices to send data to and from the internet and cloud platforms for storage, analysis, and control. So cloud platform is there in cloud-based communication protocol, while IoT is a network of physical devices embedded with sensors and software to collect and exchange the data. So IoT and second category is cloud-based communication protocol. So let us see what are the methods available under IoT and cloud-based communication protocol. So key protocols like MQTT and COAP facilitate efficient low bandwidth communication, acting as the bridge between the physical world of IoT devices and the powerful digital sources of the cloud. So MQTT and COAP, in short, what are these? Let us see. So MQTT means message queuing telemetry transport. Message queuing telemetry transport, MQTT, is a lightweight messaging protocol ideal for IoT-enabled robots and cloud applications. So this is nothing but the meaning of MQTT under IoT-enabled robots, and some robots are IoT-enabled and having cloud applications. So in that, MQTT means message queuing telemetry transport type of protocol is going to use. Second one, COAP, constraint application protocol. These are designed for low power devices. COAP facilitates efficient communication between IoT robots and cloud platforms. So these are two important or popular methods of communication protocol under the head of IoT and cloud. Next is OPC-UA. OPC means Open Platform Communication Unified Architecture. So this is a third one, third important protocol under this category, OPC-UA. Open Platform Communications means Unified Architecture. It is used in industrial automation for secure and reliable data exchange between the machines and cloud servers. So in industrial automation, if you want industrial automation and secure and reliable data exchange with the help of IoT and cloud base, then we can use OPC UA, Open Platform Communication Unified Architecture. So after seeing all these four important communication protocol, then let us see what are the other methods of communication. These are the methods of communication. Number one is infrared communication. So in robot to robot communication, infrared communication is mostly used. This method, infrared communication, uses infrared light to transmit data between the robots. Infrared communication is a good choice for short range communication as it is not affected by obstacles such as walls. So wall is not a criteria for obstacle in case of infrared communication. So by infrared light, the data transfer is possible in robot to robot communication. So it is a good choice for short range communication because it is also the advantage is that it is not going to affect by obstacles. Infrared or LED emits infrared light that can be used for transmit data between the robots. This method is handy for indoor environments with unreliable radio waves. So sometimes radio waves are unreliable. Then at that moment, we can go with this important method, infrared communication, because it is handy for indoor environments. Infrared detectors receive infrared light and convert it into electrical signals, allowing robots to decode the transmitted data. So in this word, we can see the meaning or we can see the idea of how the data is going to transfer with the help of infrared lights. So infrared detectors are there and infrared detector receives infrared light and convert it into electrical signals, allowing robots to decode the transmitted data. So this way, this infrared communication is possible. Then ultrasonic communication, ultrasonic waves. So this method of communication uses sound waves to transmit data between the robots. So this is a sound waves, application of sound waves is there for communication between the robot. And ultrasonic communication is a good choice for medium range communication as it is not affected by obstacles such as walls. Again, wall is the example of obstacle, and that is not a affection criteria for ultrasonic communication. So ultrasonic transmitters generate ultrasonic sound waves that carry data. So ultrasonic transmitters are there. They carry the data. These sound waves can travel through the air and not affected by obstacles, as I have already mentioned this. And ultrasonic receivers detect and convert ultrasonic sound waves into electrical signals. As again, these ultrasonic waves are going to convert uh, into the electrical signals, and these electrical signals carries the data which enables robot to extract the transmitted data. So this is nothing but one of the method of communication between the robot to robot communication is possible because of ultrasonic waves. So ultrasonic waves or sound waves can be used which travels through the air, and ultrasonic receivers are used or detectors are used to these detectors convert ultrasonic sounds into electrical signals, and after that the data is going to be uh, transmitted or received by the received between the or exchange between the two robots. Third important way of communication is nothing but visible light communication, VLC. So in VLC, this method of communication uses visible light to transmit data between the robot. So this method of communication uses visible light to transmit the data. So VLC is relatively new technology, but it has the potential to be very efficient and secure. So VLC is nowadays it is a important new technology, and it is having a potential to be a very efficient and secure and efficient way of communication. So visible light LED emit visible light that can be modulated to encode the data. So This method is still in its early stages of development, but has a potential for high-speed communication. So visible light communication is in the stage of development, but it is seen that it is having a wide potential for high-speed communication. So visible light detectors receive visible light and convert it into electrical signals, allowing the robots to decode the transmitted data. Now we'll see that in every kind of communication, like visible light communication, infrared communication, ultrasonic communication, electrical signals are produced. So in this category also, visible light detectors are there and they receive the visible light, and these visible light detectors convert this visible light into the electrical signals, allowing and robot decode these electrical signals to transmit and get their required data. So in this way, visible light communication is another method of communication between the robots. Now, very in shortly, we are going to coming to the last topic actually, how to select the right robot communication protocol. Uh, Choosing the right communication protocol for a robot depends on several factors, uh, including application type, environment, then compatibility with the existing system. So in the last slides we have seen different methods of communication protocol: wireless communication, then IoT based, then what we can say, cloud based, after that other methods also. But from that, what to choose, that is important, and it is going to depend on the several factors, like application type, environment, and compatibility with the existing system. So first important criteria that we should keep in our mind for selecting the right robot communication protocol is data transfer speed. So data transfer speed is nothing but first criteria. So real-time applications such as autonomous vehicles and robotic surgery require high-speed communication protocol. So this is one of the criteria for selecting the right robot communication between robot communication. So real-time applications such as autonomous vehicle require high speed of data transfer, then high speed communication also in case of robotic surgery. So in that way, this is one of the important first criteria to select or to get right robot communication protocol. Second one is wired or wireless. So what to choose, wired communication protocol or wireless? While wired protocols like CAN or RS-485 provide stable and secure connection, and wireless protocols like Wi-Fi, Zigbee offer greater flexibility for mobile robots. So depends on again the compatibility with the existing system, then the application type. So this is another selection criteria: whether to go for wired communication protocol or wireless communication protocol. It depends on the application type and compatibility with the system. So in wired communication protocol, CAN and RS-485 is important, and wireless we find that Wi-Fi and Zigbee can be used because they offer greater flexibility for mobile robots. Third important criteria for selecting the right robot communication protocol is security. Security is important nowadays. Protocols should include encryption and authentication mechanism to protect against cyber threats, particularly in industrial and IoT-enabled robots. So security is the third important criteria for selecting the right communication between the robot. So first is data transfer speed. Second one is wired or wireless, whether to go for wired communication protocol or wireless communication protocol. Third one is security. So because nowadays this is important criteria. Scalability. Fourth one is the scalability. For multi-robot systems, the protocol should support seamless communication among numerous devices without significant data congestion. So scalability, in this way we can get an idea because for multi-robot system, the protocol should support seamless communication, without any kind of obstacle, seamless communication among numerous devices. So in that way, we have to consider the scalability of the system. And as I have mentioned, compatibility. The selected protocol should be compatible with the existing components, cloud platforms, and IoT framework. So, cloud platform, Internet of Thing based frameworks, these are nothing but compatibility modes. And on the basis of that, whether we go for which type of protocol, it depending on the compatibility. So, the selected protocol should be compatible with the existing robotic system or robotic components, cloud platforms, and IoT framework. So in short, we are going to the end of this my small presentation. What should be the conclusion? So robot communication protocols are the backbone of modern robotics, ensuring seamless data exchange between the system. Whether you are working on industrial automation, smart homes, or autonomous robots, selecting the right protocol is essential for efficiency, security, and performance. So these are nothing but the concluding remarks in my presentation. Because robot communication protocols are the backbone of modern robotics. Without proper robotic communication protocol, we cannot ensure the security. We cannot go for efficiency also. We can establish good robotic system with the help of proper robotic communication protocol. So whether you are working on industrial automation or smart homes or autonomous robots, selecting the right protocol is essential for efficiency, security, and performance. So in this way, we have seen a lot of important topics related to the robot communication protocol. In short, particularly wired communication, wireless communication, IoT and cloud-based communication. After that, infrared communication, then ultrasonic way of communicating between the robots, and this way we are now at the concluding stage. So this is the in short the communication robot. What is the important details related to robot communication protocol. Thank you so much, sir.
Any question? Hello.
Yes, sir.
Yes, sir. If participants have any question, then they can ask. Okay, then.
Any question from please? Any question from the audience, sir?
If the audience have any question, then please reply.
This is a LoRaWAN. This is a Zigbee. Then this is a Bluetooth. Then this is nothing but important robot communication protocol. Wi-Fi is there. Wireless fidelity. Then we can go for this wireless communication, Bluetooth, Wi-Fi. Then wired communication, we can use control area network, RS-232, RS-485, Modbus is there. After that, Ethernet is there. So is there any questions, sir?
Okay, shall we conclude, sir?
Yes, sir. First of all, now I am very much thankful to the chief patron of this FDP, Dr. DM Yadav, sir, principal. And after that, the coordinator of this Atal FDP, Dr. Harjit Pawar, sir, is the head of the department and associate professor. I am very much thankful to Harshal Rane, sir, for giving me the opportunity to present my information or sharing my information on the topic robot communication protocol. So all I am also very much thankful to entire team of this organizing committee of ATAL-FDP on the robot communication role of robotics and mechatronics in the industry. Thank you so much, sir, for giving the opportunity.
Thank you, sir. It's a great pleasure to thank you, our special guest, Dr. A.D. Vikhar, for his excellent talk on how robots talk to each other. Dr. Vikhar, sir, you made a complex topics is so easy to understand. We learn about wired communication and how it's like a phone with a cord, a very reliable experience. You also explain wireless communication, which is like a mobile phone, giving robots freedom to move around. Finally, you showed us how Bluetooth helps to robots connect over short distances, like using a headset. The part of your talk that really opened our eyes was about IoT and cloud-based communication. You explain how robots aren't just communicating with each other anymore. They are connecting to the internet and the cloud to become even smarter. This allows them to collect huge amount of data and use powerful computers in the cloud to make better decisions, whether they are in factory or exploring another planet. Your talk was not only informative but also very inspiring. You help us to see how these different technologies work together to make modern robot possible. On behalf of everyone here, thank you so much for sharing your valuable knowledge with us. We truly appreciate your time and your wonderful presentation. Thank you, sir. Thanks.
Thank you so much, sir. Thank you.
Thank you, sir. Participants are requested to stay connected. Next session will be started within 10 minutes at 7:30 p.m.
Hello, I'm audible. Hello,
Yes,
hello.
yes, sir, you are audible.
Thank you.
Yeah.
But your voice is, I mean, low, a bit low. I'm perfectly audible?
Yes.
Yes, sir.
Yeah, thank you. We may start then, okay?
Just minute, sir.
Just
Yeah.
1 minute, sir.
Okay.
रेकॉर्डिंग चालू केली का हा केले ना बस अजून केली चांगल्या थोडं दोन चार
Good evening to all present here. Myself, Professor H.G. Sawant. It is my pleasure to introduce our distinguished speaker for today's session, Dr. Kiran S. Bole, a renewed academician and researcher in mechanical engineering. Dr. Bole, sir, is currently an associate professor and dean R&D and PGP at Sardar Patel College of Engineering, Mumbai. He received his PhD in mechanical engineering from the prestigious IIT Bombay. His research interests include fabrication of microstructures using bulk photopolymerization, fluid shaping, and development of flexural systems. Dr. Bole has an outstanding publication records with over 48 peer-reviewed journal papers and 51 conference papers. He has successfully led numerous sponsored research projects from DST, SERB, ANRF, ARDAB, CSIR, TechUp Second, TechUp Third, INUP IIT Bombay, and University of Mumbai, totaling around 5.4 crores. He is also coordinator of a 7 crore DST sponsored Nidhi Prayas Lab in collaboration with Sardar Patel Institute of Technology and Sardar Patel Technology and Business Incubation Center, SPTBI, Mumbai. Dr. Bole is recipient of several prestigious awards, including the ASME Best Paper Award at IDETC 2022, held at St. Louis, USA, and the Best Researcher Award from IE Navi Mumbai Local Center in 2022. He has conducted several national level faculty development programs under AICTE-ATAL-FDP and also served as guest editor for Springer's International Journal special issues on interactive design, manufacturing, innovation, and emerging technologies. With his remarkable academic and research contribution, Dr. Kiran Bole is well positioned to share valuable insights in today's session. So on the behalf of our institute, I request to all participants kindly join me in extending a very warm welcome to Dr. Bole sir. Now I request to Bole sir, please.
Thank you, sir. Just a word of confirmation. I'm audible to all?
Yes, sir. You are audible.
Yeah, perfectly audible, right?
Yes.
Yeah, and my screen is visible to all?
Yes, sir.
Yeah, thank you. Thank you for the word of confirmation. And so let us start this proceedings for this session 6. And as this program is on 3D printing and it is sponsored by AICTE-ATAL, AICTE-ATAL has the great initiative and really it helps disseminating the knowledge to the greater audience. So thanks for AICTE-ATAL for this particular initiative. Also, thank you to the Yevla College for organizing and writing this proposal and getting this particular program from the AICT and serving you all, the audiences, and giving me the opportunity to present something which I have done on the 3D printing. Okay, so it was told to me like to talk on 3D printing related to some advanced topics, and I thought to share you with the two latest technologies in the 3D printing, and rather I'll very specifically call as 3D microfabrication. So microfabrication, when the micro comes, or the micro 3D printing, I'll call rather it as a micro 3D printing. Okay, so I'm going to talk on the two different processes on the 3D micro printing. So micro word is very, very important here. So far, you might be familiar with 3D printing, and that really prints the component in mesoscale, which you can see by naked eye. And I mean, the dimensions in general are in the centimeters or maybe in meters. But I'm going to talk with you on the micro 3D printing. Okay. And as I mentioned, the two different technologies on 3D micro printing I'm going to talk, and one of them is called as a micro stereolithography. In short, I will refer it in my presentation as MSL, and another is called as a bulk lithography, to whom I will refer it as a BL. Okay, bulk lithography, BL. So I'm going to talk about these two processes in this particular lecture, and to tell you this particular two processes were invented in the IIT Bombay laboratory. So these are some success stories. Let us say, I'll put it another way. These are the success stories of two different PhDs. Okay, so one lead to the development of on-axis micro stereolithography process, MSL, and another is the bulk lithography. So it is outcome of two different PhDs basically. Okay, let us move ahead. Actually, my slide is locked. Um, yeah, okay. So the problem comes like if it is a 3D micro printing, where we use this particular component. So micro word, when I said 3D micro printing, micro refers to in this 3D printing segment is the sizes ranging from 1 micron to 1000 micron. 1000 micron is 1 millimeter, correct? And the thousandth part of 1 millimeter is 1 micron. So you can see how tedious it is. So where I'm going to talk about the process which prints the components in the size range 1 micron to 1000 micron. Further, to get a better feel of the sizes, I'll tell you our human hair diameter is approximately 80 micron to 100 micron. So our human hair is of that size. So imagine now you are going to develop the component of that particular sizes, 1 micron to 1000 micron. Human hair, really, we can feel that diameter, but that is 80 to 100 micron. But below that is really very difficult for our naked eye to see, and we have to develop the component in 3 dimensions in those sizes. So inherently, when you are going to print some of the component in those sizes, and you can't see it, when the manufacturing is happening, so it has a different challenges. Size, invites many challenges. So I'm going to talk about all those, how those challenges are taken care while development of the MSL and the bulk lithography, nothing but the BL. But the question comes, if we are printing those 3D micro parts, where they are used. Okay, so they are used extensively in micro electromechanical systems. So this slide tells us about the micro electromechanical systems, that's MEMS, and we live in the world of MEMS. Perhaps you might not be noting it, but yes, we are living with the micro electromechanical system. The classic example where the MEMS is extensively used is nothing but our mobile. you would have experienced or might be using, the mobile, to count your footsteps in a day. There are several apps present, in a gallery. And if you put that app in your mobile, then it gives you the count how many steps you have walked, when the mobile is in your pocket. So how the mobile calculates that how many steps you counted? So that's nothing but because of the micro accelerometer that you are having in the mobile. So that helps in counting, the steps that you have walked through. And you might have noticed it through the app, or you might be using it also. Another classic example where MEMS is extensively used is nothing but the automobile, a four-wheeler typically. I'll tell you, 10 years or 15 years down the line, the where airbags were the rich feature in the automobile, but now it's a mandatory feature in automotives. Now, in this particular norms of the present time, um, airbags is almost in every segment of the car. Okay. And now I'm not sure now airbags are mandatory on the rear side also, rear side passengers. Okay. So airbags is almost now in every car that we can say. And not only airbags, but there are many sensors. If you can see the dashboard of the automobile is flourished with many more sensors. If you are taking high-end car, it is having so many sensor. It gives you exhaust gas, it gives you crash sensor. You can see on the back side how much is the distance your car is from some kind of the disturbance. You can really see the tire pressure. You can have the braking and all those kind of the sensors, then you have auto lane changing, and so many sensors are there. All those are miniaturized. And all those are miniaturized. Everything is compact, miniaturized, and presented and giving you the output of that on the dashboard. You did not to worry about when to have the fuel to fill. It gives unit pop-up if you are taking high-end car. It pop up when the pressure in the tire is low. It pop up, you have to fuel the fuel, or you have to push the air into the tire, and so many other things. So if you are taking the high-end car, you are blessed with many sensors. All those are the micro electromechanical system where you are using the micro component. Uh, then third example classically is nothing but the few of the medical kits, like the diabetic kit is almost in 60% houses nowadays in India. Quickly you can test your sugar level through the blood. And it's a again that sensing part is nothing but the micro part and micro sensor, which is nothing but a classical example of the micro electromechanical system. In industry, typically in robotic industry and automation industry, again, there are many sensors, and all those are miniaturized. All those are classic example of MEMS. Why I'm telling this, is uh, many of these parts are fabricated using the 3D printing. And that's the 3D micro printing especially. That's the motivation. Why we should go for the 3D micro printing. So these are all applications. These are all are developed, few of them are developed by the 3D micro printing. There are many more processes into the MEMS, but 3D microprinting is one of them, and I'm going to talk on one of the two of these processes called as the micro stereolithography and the bulk lithography. Okay, as I said, the in you for human body, many things we have to measure, and all those for measurement of all those, how is our body functioning. Even our inside organ, its conditions and etc. also will be seen by some of the devices you can send through um, mouth into the stomach, and then it can scan. Sometimes surgery is also happening if you have the robot of that tiny kind. So system level development also happens. So you not only are developing the component out of the 3D printer, but you also can develop the systems which can do many things for you and you need not to have the surgery to happen. It can operate, without the surgery. So many things, and not only that, but monitoring your body. So many sensors are being there, and that are all are miniaturized and nothing but the MEMS. And in MEMS, one of the process is nothing but the MSL and the bulk lithography. So let us quickly move to the first process of the 3D microprinting. That is nothing but the micro stereolithography. In short, I am going to refer it as a MSL. I don't know whether you have gone through the stereolithography in the previous the lectures. So far, 5 sessions are already being covered, and this is sixth one. But I'm sure that generic 3D printing process, some of the speaker would have definitely covered to you. So what we do in the 3D printing, the generic process remains same. So what we do in the 3D printing is, first of all, we develop a CAD model. Okay, whatever the component that we have to develop, we develop a CAD model of it. And for this development of the CAD model, we can use any software. We can use AutoCAD, we can use CATIA, ProE, anything, which develop. There are so many things, Creo, so many softwares are there in the market, and you can use any of that software to develop the CAD model. Okay, so we develop that CAD model, and as a first step in the 3D printing. And that is a pre-processing step, but yes, it is the first step. The process starts with the development of a CAD model, and we take the help of many commercial softwares. What we do after development of the 3D CAD model is we have to save it in the machine acceptable format. That is, we are going to print it. So the 3D machine acceptable format, and that acceptable format is nothing but the .stl. So .stl is commonly being accepted. So we save the file as .stl. As we know, when we are operating on Windows, we have so many options, MS, or you want to save the file as a .pdf and everything, and many more. So here in the CAD modeling software, they have their own extension. But important is, for when you want to print 3D print, machine accepts the file in .stl format. So we have to save it into the .stl. Okay. So now the 3D model is ready. Let's say here we have developed the cone. That is what actually the component which we have to print. Okay. So we develop the cone in the modeling software. We have saved it in .stl. But when we have to print it, we have to print it in additive way, layer by layer. This is a 3D component. So what we have to do is we have to slice it and make it into the 2Ds. So let us say the two slices mentioned here. So we have to cut this 3D cone into the two slices. It is a illustrative purpose. Actually, the important is, for more resolution and accuracy, we have to slice as number as possible. As number as possible means infinite is ideal, but infinite we can't do. It will take infinite time then to produce it. Okay. So we have to see so many parameters are there. I will not discuss those all in detail. If someone is having really the doubt how many slices we have to do, really we can have that in discussion. Okay, but yes, we have to optimize how many layers to produce. And there are many more parameters on which we decide how many layers we have to do. So we slice in that particular layers. Here we have illustrated the two slices. One is pink slice here, and another is the blue color slice. So when we sliced it in a pink color, then we get this circle, and the blue, we get a blue like circle here. So these are the two different diameter circles because it is a cone. Okay, so we slice at that particular location, and we get the slice planes here. Now, what we do is we are going to fabricate these circles in layer by layer way on a machine, which is called as a micro stereolithography. In short, what this machine consists of? It consists of the laser. So there are many laser systems such as argon ion, CO2, ND-YAG, and so many other. The typically, I refer to that this is the outcome of two PhDs in which took place in IIT, and there we use the argon ion laser. But argon ion is not only the laser system, but there are many, as I mentioned. So the argon ion laser we take, and then there is a switch. switch, optical switch. So optical switch make the light to pass or not to pass. So it's a 1-0 function. Like in switch in your at your home to make the switch on and off for a bulb. If it is on, bulb light get on, lightning happen, and off, then lightning is not happening. So it's a 1-0 function. So switch is like that. So when it is on, light will go pass and it will fall on the mirror, and mirrors are mounted on XY scanner, and XY, I mean the actuator or the motors, and because of this, it moves in X and Y direction. This mirror moves in X and Y direction. It falls, so the laser falls on the mirror, from where it goes past through the focusing lens and then get focused on to the free surface of the resin. Resin means what? Resin is a liquid which is a monomer plus photoinitiator. So let me tell you about resin. Resin is the photochemical basically. So it absorbs the light, and to absorb the light we are having the photoinitiator. So this resin system consists of the monomer plus photoinitiator. It's combination of that. Generally, for the argon ion laser, which is used and having the frequency of 351.1 nanometer, for that purpose, for absorption of this light, which is emitted UV light, 351.1 nanometer, typically the monomer suggested is hexanediol diacrylate plus the photoinitiator. Photoinitiator is mixed in 4% by weight into the hexanediol diacrylate as a monomer. So by that way, this monomer is prepared, and when the light falls onto it, photoinitiator, that is a benzoyl ethyl ether, absorbs the light, that UV light, and cross-linking happens. So chain reaction takes place, and thus monomer turns into the polymer. So when cross-linking happens, then liquid turn into the pure part, that is solid phase. Okay, so what we are going to do is we are selectively and directing this focus light in control way so as to form this circle. So when we are slicing, we are getting the circle. It's not only the job done. What we have to do is this focus light we have to scan. So this is a line scan. So the focus spot is scan like this, and when it is scanned like this, look at this. This is a one line and scan over, in XY plane, and we have to print only the circle. So if we consider this line, few part of the line is outside the circle, few part is inside the circle. So whenever the line is inside the circle, that time laser should be on, and whenever the part of the line is outside the circle, that time the focus spot, it should be off, I mean to say. And that's why we are having the optical switch. Okay. So once this CAD model is done, we are slicing it. And after slicing, we are generating the scan path for each of the layer. And when we are generating the scan path, basically what we are doing is nothing but generating the data of time versus position X, Y, and laser condition on or off, 1 or 0. So we are having an array of data, time at time t, where is the laser at X and Y position, and laser state, whether it is on or off. If it is here, X and Y location at that particular time, and laser on. If it is here, then at that time, X and Y position and laser is off. So like that, we have to generate a lot of data. Okay, for each of the layer, it's not only for one layer, for many layer, because every cross section is different as mentioned here. Okay, so for each of the layer, we are generating this data. And after generating this data, we are sending this data through a microcontroller to the X and Y scanner. So the time t and X data is sent through the microcontroller to the motor X. Time t and Y data is sent from the microcontroller to the motor Y, and time t and laser on off data is sent to the optical switch. So this is automatically controlled through the microcontroller, and then when the focus lights scans in this way with that kind of a data, then you are getting the circle form. So initially this platform need to be very, very close to the free surface, and first layer is get formed, and upward once it get formed, then you are stepping it down. So once you step down, then again the fresh liquid comes over, and when fresh liquid comes over, then you are sending the second data. Okay, second layer data. So you're getting the second layer, which is stacked on the previously formed layer. And that's why we call it additive manufacturing. This is why we call it as additive manufacturing. So we are placing one layer, another layer, and so on. We are going on and on for the layer which we target for getting this component to be fabricated, and we stack together, then we get this component. Okay. The interesting point is that the laser light which we are having is having the Gaussian intensity distribution. It's not the square or circular. It is having Gaussian intensity distribution. Also very important one is this is the chemical, this curing, as I mentioned, when the light falls onto it, cross-linking happen, and cross-linking means photopolymerization starts, and you are getting the solid part. And this never happen at any energy. For this to happen, your energy should be something, okay, some value, right? It should be beyond some value, I mean to say. Where that is beyond some value, that value of the energy is called as a critical energy, critical curing energy. So whenever your energy of this light is beyond certain energy, which is prescribed for that chemical or that resin system, then only the cross-linking is happening. So when again at some energy level, the curing will not happen. Only if it is beyond critical energy, then only curing will happen. And when curing happen, then it gets into this shape because it is Gaussian in nature. Okay, so you don't get the rectangular or something like that, square or something perfectly cornered, I mean to say, straight, I mean to say. It won't be. It will be the Gaussian in nature. So these are many more things. Further, you can't go too much of below, because then your light is being absorbed by photoinitiator, and you really can't go much below, and that's why it limits the layering thickness. So many parameters which decides the layering thickness. Okay, how much the layer thickness that you should have. So many. Again, the lateral surface. If you give a lot of big layer thickness, yes, your component will get produced fast, but it will take a lot of time. Sorry, it won't take a lot of time, but yes, your lateral surface won't be very smooth. Okay, so how is our the optical arrangement? So we are having argon ion, and then from argon ion laser, the laser comes, it goes through the acoustic optical modulator or switch, I mean to say, and then there is a pinhole. Only one light will be passed through the pinhole, and then we are having the mirrors mounted onto the motors, and through this mirror, then the light is passed through the lens and onto the resin surface. So this is the arrangement. Look at this. This is a schematic diagram of the MSL system. So for CAD model, really we need a computer, right? So computer with the CAD software that generates then all data after slicing and scan path. That particular CAD data is then passed through the microcontroller. As I mentioned, we generate the data of time t versus x, y, and laser on-off condition that is sent to the microcontroller. Microcontroller takes the time t and x data and send it to the x motor. Time t and y data send it to the y motor. Time t and laser on-off data for that is sent to the acoustic optical modulator, which makes the laser on and off, and it works in synchronized way. And when it works in synchronized way, then we get this component form by layer way. One more very important, once the layer is formed, then we have to take this platform down. So we are having one more stage called as a Z stage. So XY stage is for scanning the focus light, and Z stage is after first layer gets developed. Then to step it down, we are having the Z stage. That also can be controlled through the microcontroller, or you can have manual as you wish. But manual, then your intervention is required and your presence is required. So better it is done through the a microcontroller only. Okay, so we have seen these various techniques so far, and you know, it's very important to tell you, you know, it's not only one MSL type focus spot being scanned over the resin surface. Rather than focus spot, what we can do is we can really project the entire layer. Like let us say this is what actually if I want to if I want to produce this circle from the focus spot which is being scanned, rather than scanning a point, what I can do, I can project entire circle. I mean light, having that light into that circle, you know, projected directly onto this resin surface. Like our projector, you would have seen, I mean definitely would have seen the overhead projector in the classroom when we project the PPT on the board or some screen. Like that, this entire 2D can be projected onto the screen, and in one go we get the entire circle, rather than focus spot scanning, and you're scanning entirely and generating the one layer. So it's a time consuming, but the advantage of the focus spot scanning is that you can print small component very precisely and accurately compared to the projection micro stereolithography. Projection stereolithography, you don't have the accuracy, comparable accuracy or competitive accuracy as compared to the focus spot scanning system. Okay. Another very important, as I mentioned to you, that the laser is being scanned in X and Y direction. Okay. So when laser is scanned in X and Y direction, how we can scan it? So this is a very simple mechanism. If the light is coming onto the mirror, what we can do is mirror we can tilt, and when we are mirror we are tilting, the laser will automatically move in the linear direction. Okay, this is as simple as that. Rather than, you know, anything to have extra, we can just tilt the mirror. So mirror tilt, if we tilt the mirror, the light really can go in the direction plus and minus. Okay, this is the simple. So you tilt in one way, it moves in one kind of axis. If you tilt in another orientation, then it moves in the another axis. So that's how you can have the different tilt orientation and cover the both x and y x and y axis. But the problem with this tilt is that when you're tilting the light, then focus spot do not remain constant over the resin surface. You see, if this is the resin surface here, then the focus spot do not remain constant. Focus spot, this is a locus of the focus spot. So when the focus spot do not remain constant on the resin surface, and I mean there is only one point where the focus spot will remain constant, and all other point I can say it's a deep focus spot. So when it is a defocus spot, and if it is a defocus spot, your energy is not concentrated, I mean to say. And when energy is not concentrated, it's not sure that energy will be beyond critical energy or threshold energy, as I mentioned, for required for the curing. So curing may not happen. So when you are going with this kind of a scanning scheme, it's not sure that your curing will happen always at any lens. Okay, so you have to have the focus spot constant on the resin surface, but this typical mirror tilting will not make the focus spot constant in the x and y direction. But still people used it extensively because you're doing micro component, you're developing a micro part. So in micro part, you are not worrying about, you know, developing the big size component. But yes, sometimes we require long component. I mean, the classic example is the PCB. On PCB, you are having line of micron width, but length is too much. Length is in centimeters. So we really can't go with this kind of the mirror tilting kind of the uh, concept. This mirror tilting concept is called as the galvanometer scanning, and people use this galvanometer scanning in different orientation. Let us see this. Here you are having laser light and lens first and mirror later. So laser comes and pass through the lens, and then you are having focus spot, and it falls on the mirror, and mirror is tilted, and you get it scanned over the xy plane. And another is this, you are having laser and then mirror and then it passed through the focusing lens. So mirror first and then lens later. This is called as a pre-objective. Mirror first, lens first and mirror later. This is called as a post-objective. In all these cases, it's very logical that your focus spot do not remain constant all over the resin surface. Okay. So it increases the spot size for larger scan length, and scanning by mirror rotation is not going to help if you want to produce a component of larger length. Then people come up with another idea. They remove the mirror, only the lens is being used. So what they have done is they have the laser source and they have moved the lens and the mirror is being removed. So but the problem is, when the laser is not coaxial with the lens axis of the lens, then again the spot will be distorted. Intensity profile will be distorted due to off-axis motion. So this off-axis, and because of this off-axis, the intensity profile will be distorted. But the people typically in China, they tried first time. What they have done is, so they removed the mirror. Mirror is not being used, but and the axis of the lens and the axis of the laser is same. And rather than everything is fixed here, and rather than moving anything like lens or mirror is of course not at all here. They moved the tank. So this is called as a photoreactor tank scanning. So they moved the tank, and when they moved the tank, the problem is in the tank there is a resin which is the liquid, and when you are moving the tank, there will be wave formation, and it creates the wavy microstructure due to the motion of the resin which is present in the tank. So if you want to counter that, then what is the remedial is, you move the tank with a very, very low speed, so that waves won't be so much of insidious nature. Okay. So this is the, but this impose the limitation on the speed, and if it is a limitation of speed, really you can't fabricate the component in a short time, I mean to say. And of course, when we learn all those, we have seen all those like pre-objective, post-objective, off-axis scanning scheme. In every of these cases, we can see that the intensity will not remain constant at 0, 0, and it will get diminished, intensity quickly at the other places. You see here, even, at 0.5 mm or 1 mm, your intensity is almost reaching to 0. 1.5 almost reach to 0. So this is the problem, that we cannot print the large size component, micro feature, but large scale, large in length. Like on PCB, you are having lines which are in micron in width, but length is in centimeter. We really can't print all those kind of a thing. Okay, and then this is typically simulation, which is sim experiment and simulation being shown, as it is logical. So still the experimental observation is captured and compared with the simulated thing. Now this on axis. So how to do the printing of the 3D micro printing of the component, which is micron in size, in width, let us say like in PCB, but length is too much. So the people come up with the on-axis scanning scheme, and this particular part was a part of like PhD to my senior at IIT, and he is Dr. Suhas Deshmukh, and basically he invented this. His contribution was use of this on-axis scanning scheme and deployed into the 3D microprinting. So what is done in the on-axis scheme is, you are having a laser which falls onto the mirror, let us say M1 and M2, and there you are having a lens. So arrangement remains same, but what he did is look at this animation then. In first case, for scanning in the Y direction, what he did is he moved the mirror 1 and the lens on the axis here. So if he moved in this way, rather than tilting, he moved the lens and the mirror completely on the laser axis coming in this direction. So when it's there, when it is a moved like this, focus spot remain constant throughout the y-axis. Okay, it's not tilted, it's moved now. Okay, so focus part will remain same. Now what about the y-axis? So what he did above for the y-axis, he moved the both mirror M1 and M2 and lens together. Look at this particular part again. See how he has done. Moved M1 and M2 and lens, right, together. So when he moved together, in x-axis also the focus point remained constant. So this is called as the on-axis scanning scheme. This is concept. So with this, the uniform spot characteristics is achieved. No wavy microstructure as compared to in the photoreactor time scanning we have learned it. Now this is logical. So you go at any distance, your focus spot will remain constant with this on-axis scheme, but in all other scheme, your focus spot really is bigger in size. In on-axis scheme, your intensity is constant. In all other scheme, your intensity diminishes very fast, and is seen through the experiment work and simulation also. You see, this is the actual uh, the dimensions, and this is simulation. So focus spot remains constant. Okay, intensity remains constant. Focus intensity remains constant. Focus spot remains constant throughout the scanner range. Okay. Now these are the four linkages B1, B2, B3, and B4. Let's say how now this concept is realized really. Okay. So this concept was basically Suhas has taken from the CD-ROM, and nowadays it's unfortunate we can't see CD-ROM, but yes, it is we are fortunate that we moved ahead of the storage capacity, and that's why the CD-ROM is not in our computer system. But definitely you would have seen the CD-ROM. It's not the era of large where when the CD-ROM were there. Okay, so you would have seen the CD-ROM where we used to put the CD where there is a data, and to read the data which is present on the CD, there is a laser, and the laser is being scanned over the CD accurately, and because of that we will be able to open the file as desired. Now, what is the mechanism used in CD-ROM to scan that laser light on the CD surface is nothing but the flexural mechanism. A flexural mechanism consists of these four linkages, and with these four linkages, the outer linkages are fixed, inner linkages are free, and on one of the inner linkages the force is applied. And when their configuration is like this, when outer links are fixed, all links connected to a rigid body here, and when the force is actuated here, as it is a compliant mechanism or flexural mechanism, they bend themselves. They are not rigid links, but ensuring this design configuration ensure that this body always moves in a straight line. Okay, and I think the participant from mechanical engineering can understand well, but other branch discipline also can logically think. Okay, how the things work, and for them actually I presented this particular slide. So if let us say if you are having this link here, flexible link, okay, and it is fixed here, this link is flexible, and the force is applied here. What will happen as this link is flexible? It will bend. This body will take a new shape like this. This is a line of action of force. And now this is the center of the body. And center of the body new is here. Previous center, new center, there will be some error. And that is called as a parasitic error, epsilon. Sure, the displacement is not in the direction of the force. Second, if there are two flexible linkages and there is a connected to a rigid body here, and two links connected firmly here, fixed here, and these links are flexible. Now the force is applied here. The body will take new shape like new shape, and it is like this here. Still, there will be some parasitic error. The center of this block in new position and center of this block in previous position. Okay, there will be some difference, and that is called as a parasitic error. So this combination also will not work when we are going to use this kind of the flexible linkages into the microprinting. and concept of on axis will not happen. So what then next is the fourth configuration. Now the four linkages here, and outer linkages are fixed at AA. All four linkages are rigidly connected to rigid body here. And then these are the internal two links to whom the body is firmly connected here. And the force is applied. As these are flexible linkages, they, they bend, and this body takes a new shape, and they're perfectly aligned. The new shape, or the body takes the new shape, but it is in perfectly aligned or perfectly in the direction of the force F. Okay, so this typically, when you're applying the force, the body moves in the direction of the force only in the configuration 3. This configuration, first of all, was invented by the Shaurya at MIT, USA. Okay, and commercially, this mechanism was used first of all in CD-ROM. And what Suhas did when he was working for development of the MSL, he used that concept of CD-ROM in using this on-axis scanning scheme for the 3D microprinter. So he uses this, and he developed this particular drawing and developed this complete mechanism. So this is his system. The first system, photograph of the developed MSL system. There is a laser source. This is the argon ion laser, and then you are having mirrors. Then here is the four linkages on which we have the mirror M1 and M2, and then your focus spot is acting here. So this will be better picture to see. These are the two M1 and M2 mirrors, and the laser light comes and get fall over here. You look at this, when the force is applied and the body moves exactly in the same direction, and because of that, there's no parasitic error. This is the data acquired in X and Y while X and Y scanning. Blue line is a reference and the green line is actual, and you really can't see the distinct difference between the blue and the green. It is so accurate. The error is likely to be more at the corner. Okay, when it is a suddenly turn in 90-degree in other axis. So this the corner is magnified and presented. Then you will be able to see the error. Look at this. There is a minus 800, and this is minus 800.5 micron. Means this is a 50 micron. Okay, yeah, 0.5 micron. I mean to say. So 0.5 micron means 500 nanometer. Right, so this is 500 nanometer, and is fraction of 500 nanometer. So see, this is my nanometer basically. Okay, here also you are having 0.25 micron, means 250 nanometer. It's fraction of 250 nanometer. So this is the level of accuracy that Suhas has obtained under the guidance of Prasanna Gandhi at IIT Bombay. And this is the mechanism. And now really this mechanism was bulky, and now this microprinter has been taken a shape of laptop. I mean, the complete system. This is a mechanism, but this 3D microprinter you can house it on you can hold it on your laptop, on your lap, like a laptop. Okay, so miniaturized 3D microprinter is being now in a place at the Professor Prasanna Gandhi's laboratory at IIT Bombay, and you can see these are the actuators. I mean, one is your mechanism, so that we discuss extensively. How is the advantage of having or deploying the flexural mechanism in place? But equally, flexural mechanism inherently has that capability. But this driving force from where you are going to bring. Okay, so this driving force you're going to bring from motor, whether stepper motor or any other kind of a motor or any other kind of a drive. Okay. But if you are using stepper motor, it's a rotary basically, and converting that rotary into linear, then you will use mechanical elements again, the rack pinion mechanism and so on. So again, there will be the hysteresis or the friction, and you won't get the exactly straight line mechanism. I mean, straight line. I mean, it won't be a straight line mechanism. So what to do? So at actuator level also you have to take utmost care so that the error is minimum. Okay, and the force and the displacement is in align, in exactly straight line. So what is the best solution? Best solution is to use the voice coil motors. So these are the two voice coil motors we have. And with the help of this voice coil motor, really we can have linear displacement quite well. And this linear displacement is very confined, very accurate, because we don't have friction. Because of voice coil motor, we have the magnetic levitation being in place. So as it is a magnetic levitation, there is no friction. Okay, no physical contact, so no friction. These are typical the pre-processing. I mean, even this system when it was developed, the entirely your scanning, scan path, everything was developed in-house. So it's an indigenous development, and these two students, Mr. Amit Pathak and Alim Baraki, contributed in development of this indigenous made software, their own software in this FSL system. Alim Baraki was from Ethiopia. He was pursuing masters and he contributed in development of this particular software for the slicing and scan. But his immense contribution in that part. So basically now then you are having the computer from where the scan path and line scanning everything comes, and the data is given to the microcontroller. Typically the microcontroller used in the laboratory is DSpace 1104 DS1104 platform. We have couple of this DSpace 1104 platform in the SPC as well. And then there's a CLP board of microcontroller, and DS1104. It has encoder channel, then digital to analog channel, and this is connect. These are connected to amplifier X and Y, and to the motor Y coil motor 1 and 2. And then when it moves, and then whether it moves exactly in straight line or not, so you need a feedback. And feedback can be gathered through this optical encoder and given to the microcontroller back. Microcontroller acts on the signal, and the you are having PID controller basically built into this. I mean, PID logic is built into this and ensures that the functioning is happening actually as per the data given. And then you are having RF driver typically to actuate the switch acoustic optical modulator. So this is how is your system integration taking place. These are the actual pictures of the units. This is the power supply app lab. This is RF driver for the acoustic optical modulator. Then these are the RGF and interpolator taken up from the machine from the optical sensors, Renishaw optical sensor, and these are the current amplifiers. These we have current amplifier. Voice coil motor do not work on normal current, so you required high current there, and for voice coil actuator to operate, and then you are having this current amplifier in place over there. This is a CLP board of the display system, and let us see then when these all are connected, then how it works. So this is the low speed scanning X and Y. Look at this video here. Some problem in video running, I guess. Let's see this. Yeah, I hope here you can see high speed y-axis scanning. It's moving at very high speed in the y-axis. Get this, it moves in X and Y scanning now, X and Y direction. High speed in X and Y direction. This is the voice coil motor. So because of magnetic levitation, there is no friction, so very less error. No hysteresis as well. Perfectly and is precise. So the voice coil motor number 2 for other axis, and these are the mirrors. Everything is fabricated here only. It's indigenous development. Everything done in the laboratory. Last one is high speed, large range in this window. So very large range. The movement is in span is large. Speed is also high. I hope you would have understood so far what actually I'm telling. And then you can see at high speed what are the results we have got. And almost a reference and actual line coincides with each other. So there's no really at this scale we can have the difference or the error to see. But if you magnify the corner point, then we can see the error, and yeah, we can see that the error is then uh, in some nanometer. Okay, now that's the beauty of the MSL system which is being developed. Another challenge is that when your focus spot is being there, and yeah, when you're using the focusing lens, typically the focusing lens used here where the purchase from the Newport, and Newport is very renowned and very precise, known for its accuracy and precision. And they give their own data sheet, and with that data sheet we can have the focus distance. But really, it is a test time still, because when you are when you are mounting the focusing lens um, purchased from any company and into your own system, and there will be some kind of the assembly error, and you have to verify that. So how do we verify? So at recommended focusing lens, around that distance you scan the laser at some 50 micron up and down, and see where you get the thinnest line. So that is the focus. That is the perfect focus. So that is being done, and then focus is ensured. Okay. And then after that, then the interesting thing, so far we have learned the computer engineering when we start with the computer data generation and all those scan path. You require different programming languages on all those processing the CAD file. Then electronics, your knowledge is required really from optomechatronics point of view also. Optical systems, mirror, focusing lens, and the mechanical system, electronics, microcontroller, and mechanical engineering, mechanism, flexural, and so on. Important now at the last stage, your focus spot is being exposed onto the resin system, and their cross linking is happening. So it's a photochemistry. So now the chemical engineering one more branch will come into the picture when you have to do the system development. So that's the beauty of system development. I mean, it's not only in 3D microprinting, but in any system development, you have convergent approach. You have so many disciplines involved. Like here you see, we started with computer data and processing it, and my electronics, you are having microcontroller and so many things, then optical things, then mechanical, flexural mechanism, and now the chemistry. So when focus spot falls onto the resin system, and then curing happens, and that is being tested. So this is a CAD data, and test is being conducted on to fabricate the circles of dimension 50 to 500. The bigger one is 500 micron, and smaller one is 50 micron. And every time, 4 times this part is produced as the actual fabricated part. You can see on right hand side. When actual fabrication happens and 4 times it is repeated, then then the different readings are obtained and then average is taken, and from the average then error is calculated. And further, this error is then made normalized by percentage. So this percentage is the normalized platform. You see that percentage error is changed from 1.33 to 18.45. As the size is smaller, your error is more. Size is bigger, error is less. Okay. So it's size dependent. One way we can say size dependent. With the same dimensions, if you take 500 and micron and 50 micron, but other way, in previous case, these were holes. The outer part was solid. Now here these are solid. And when this thing is there, but size remains same, your errors are different. Its sign is different. It's negative now. And but although it is a negative, but their values are also not the same. It's different. When the instead of circle, the rectangles are taken. Okay. So like the square is taken. You see the 500 by 500, and smallest one is the 50 by 50. And then your distortion values are different. I mean, size is same, but instead of circle, they are now these the rectangles. Now this again, the rectangles being the solid one, the signs are changed and the values are different. So what I mean to say here, extensively the work is conducted to understand photochemistry. Then when the light falls onto the resin and curing happens, shrinking is the part, and because of what you don't get the size which you predicted, there is some error. All those allowances then you have to give into the CAD model when you're developing. Learn from the photochemistry, the shrinkage allowance and all those estimate. And shrinkage allowance is not only size dependent, but the geometry dependent also. It is a different in case of a circle, the allowance is different in case of a square. So all those considerations you have to do, and then you will be able to print the marvelous component. And these are the few of the components which actually I have printed when I was there in the IIT during my PhD time. You see this four cone type structure. The base is 448 micron. I told you initially our human hair diameter is 80 to 100 micron in diameter. Look at this cone, and cone base is 450 micron. Actually, it was targeted in CAD model. Attained is 448 micron. Height of the cone is 423. We targeted 425. And then here in pyramid, the base is 996. We made in CAD dimensions at 1000 micron, means 1 mm. This is 1 mm actually, this scanning electron microscope, 1 mm. And the top land of the pyramid, this top land of the pyramid is 274. We made the CAD model of 275. A big size component also we produce like 4 mm by 4 mm and 4 mm by 4 mm, although it's mm, but the channels are in micron. Okay, so with this part, what we tried to demonstrate, we can fabricate large range, but feature in micron. So the channels here are having dimensions of 150 micron targeted, achieved is 146. And then counter hole here, 740 bigger one and 417 is achieved. It is a counter hole smaller one. So this demonstrates that we can fabricate large size component. So the on axis really can work for large range, but micron feature component also can be fabricated very easily. This way fabricated for observing some microfluidic applications, in the chemical analysis. Then the large tanks 4 mm by 4 mm, again this bigger one, but it is the thickness is smaller one. So micro but large range. And the inner were high aspect ratio. This small tank, but its height is more. So this demonstrates that we can develop large range and high aspect ratio structure. Okay. Important takeaway from this particular fabrication is that yes, we can fabricate. These all are demonstrations of those about the technology, what technology of MSL really can do. But the problem is when you observe under the scanning electron microscope, you can see the stair-stepping effects. One layer, another layer, you can distinguish, and we can very clearly distinguish in scanning electron microscope when we fabricate and see this lateral inclined surfaces, curved surfaces. Typically, the straight surfaces we can't see all those, but when the surfaces are inclined, we really can see all those and can be easily seen. Okay, and this lead to the another typically sorry, this lead to the another process which I'm going to talk about is nothing but the bulk lithography. So this escaping effect is not good. So people come up with the different strategies. I mean, okay, the David ETL, this group is from the Georgia Tech, and they develop the parameter estimation method. Means at the corner you can control the exposure according to the curvature and then have the smooth surfaces. Then Pulak Pandey sir, IIT Delhi, he developed the adaptive slicing methodology. One more group from USA PAN, they come up with meniscus approach. So if you want to have some curved surfaces, so what they produce is, you can have the straight surfaces initially. You can take out after layering and have the meniscus. And meniscus you form which conforms to the curved surface you target. Okay, so a lot of the fluid mechanics and structure and fluid interaction you have to study, and if you study that, then really you can fabricate those curved surfaces very easily. David Rosen and Amit Jariwala, typically Amit Jariwala also is working with David Rosen in Georgia Tech now, and they come up with a exposure control projection, thick film exposure control projection lithography. It's a projection lithography, but at every pixel you can have the energy variation to get the cured shape developed precisely at that particular location. But monitoring and controlling the precise intensity or energy level at that location is very tedious task. Okay, like in our projector, we have energy everywhere constant, but varying energy at different pixel is very difficult and tedious task. So this inverse problem, finding exposure control parameter for the desired field depth, is really very difficult. This lead to the new process called as a bulk lithography. I'll talk about the bulk lithography. So in bulk lithography, to understand clearly how it deviates from the micro stereolithography, um, so to understand that, I have taken the same component, that is the thing with the cone. So if you see this cone, the cone in the MSL, initially we have seen the base at the bottom and apex at the top. With the same cone, if you have to fabricate by the bulk lithography, the should be on the top and apex at the bottom. And the slicing pattern is also different. In the MSL, slices were done which is parallel to the base, but here the slicing plane are perpendicular to the base. And where you were cutting perpendicular to the base, considering the two slice planes, like here the red one and blue one will lead to this hyperbolite, blue hyperbolite, and red one will give the outcome of this red hyperbolite. Now, how to develop this component using bulk lithography then? The constituents or the elements remain same. We are having laser source, then switch, mirror mounted on the motors or the scanner or motor, which are driven scanners which are driven by the motors, voice call motors. Then we are having the focusing lens, and then the focusing lens when the light is passing through the focus lens, then this light is tightly focused at the interface of the transparent substrate. Transparent surface is placed over the resin surface, and focusing lens make the light to tightly focus at the interface of the transparent substrate and the resin. So we don't have the build platform which is moving after each layer down like in MSL. Here we are having the fixed surface, and the resin surface is covered by, I mean, the transparent substrate, and the laser light which pass through the focusing lens is targeted at the interface. And when it is a target at the interface, now you are scanning this mirrors in X and Y direction. While scanning it, you are fabricating this hyperbolide. But you look at this hyperbolide, when you are forming the hyperbolide, the cure depth from point to point is different. Here also you see the cure depth from point to point is different. So when you are scanning the light and targeting this hyperbolide to form this cure depth variation to get the cure depth variation, you need to have the different energy at different points, and that energy level is defined by your cure depth requirement. Okay, that's the point. So you have to vary the energy while scanning, whereas in MSL you don't need to vary the energy. Okay, energy is constant in MSL, but you are varying the energy while scanning. And when you are varying the energy, when you want to vary the energy, I mean to say, while scanning, your switch cannot be 1 and 0. Like in house, you switch on and the light get on, switch off light is 0. That function won't do. Rather, you require a regulator. Like the way you control the speed of the fan by a regulator. When the regulator is moved or then the resistance is varied and your fan speed goes vary, right? So like that, you need to have regulator which varies the light intensity, okay, coming at the resin surface. So this AOM is not having the on-off function, rather it is having the some analogous function, right? It varies the light intensity in the range, okay, and that is governed by the Q depth. Now the initial experiment is done like, so we have to establish first of all the relation between the energy and Q depth. That is not really the concern in case of the MSL. But in BL, if you want to develop the component in this way, you have to have the established relation between the energy and the Q depth. So a lot of experimentation is done and where the energy is varied linearly from 0 to some level. And interestingly, it is seen that when we vary the energy, Q depth changes. But it doesn't have that particular the pattern going along in linear direction. But at one level, then you will see that there's no more increase in the Q depth. So Q depth saturate. So after certain energy, whatever energy you're putting, the Q depth will not increase a lot. And that is called the saturation of Q depth. So this triggers to a lot of experimentation. Now the on axis remains same, but the difference is that while scanning, you have to put the energy, different energy. And again, the question comes when the system of like your flexural mechanism and you want to vary the energy. So one way I mentioned the one way is to vary the energy of the light by acoustic optical modulator. Another way is you can have switch on off, but the exposure can be controlled by having the exposure time different at different location. But that exposure time having different at different location will lead to all nonlinear control tedious, nonlinear, and complex control theory. Rather than that, using the AOM and controlling the AOM is very, very easy. So that is being done. But again, the question remains, what is the energy level and the Q depth, that relationship? Okay. So a lot of experimentation is done by varying the power in some range and then exposure time. Okay. On the resin systems, SDDA, BE and TMPT is another kind of a resin. The TMPT is also used along with the BE, and then a lot of experimentation is being done at different energy. The different cured depths or cured voxels are obtained, and all those cured voxels are taken up, and then we have to wash that cured voxel, because when you are taking out, then there will be all the uncured resin surrounded by, and that uncured resin we have to clear first. So lot of like again the experimentation was done, which is a good method and all. We use very simplified method using a tissue paper, like in hotels and all, at the home also we will use the tissue paper. The tissue paper, you put it on the glass and then it soaks the uncured resin, and that methodology is very simple methodology rather than all the uh, different methodologies when we started with on tackling this particular problem. And there are so many sophisticated and rich methodologies that were mentioned, like having a chamber and then having some kind of the T-butyl alcohol will solidify and then vaporize it, and all those like complex systems were being proposed. But we come up with a simple idea, if uncured resin is there and how to get rid of it, like put the tissue paper, it will soak very easily, and you can then simplify the drying of or carrying away this uncured resin. Further to clear it, you can have 1 or 2 drop of acetone by keeping this glass on the wedge and have the clear the voxel, and that can be observed under microscope, and you can record how much the depth attained for the typical energy. Okay, and then this is the mathematical model which is being developed and typically called as a cure depth cure depth model. And this experimentation I will just skip a bit, okay, because it's a more of the mathematical. Someone who is interested into can contact me separately and we can have a discussion on that. Another is when we are forming this the free form surfaces below the glass, below the transparent substrate, I mean, then the lower surface is typically a rough because you are putting a lot of energies there, so it's not as smooth. So again, experimentation is done and to see that how much is the surface roughness being achieved at the underneath this glass substrate, and then that all those characterization is present. One more very important point I missed here in bulk lithography is to tell you that with this particular strategy, you need not to process like in the conventional layer by layer way and multiple layers, rather than only in one 2D scan you are able to generate the entire component. So look at this, one line scan, you are getting this hyperbolite. Second line scan, you are getting another hyperbolite. So only in one 2D scan, you are able to generate entire 3D component. Whereas in MSL, in one 2D scan, you are able to generate one circle, which is one layer. And you have to have multiple 2D scan to generate the 3D component. Rather than that, here in one 2D scan, you are able to generate the entire 3D component. That's why this methodology is called as a bulk lithography. So unlike all other the 3D printing processes, this is the very distinct process. In only one 2D scan, you are able to generate the entire 3D surface, and that's why it is called as a bulk lithography. Okay. And then sir, this surface characterization is being done. And then look at this at photochemistry again. So what is happening in bulk lithography when the laser light comes and we shine it at the interface of the transparent substrate and the resin. Resin is having monomer, photoinitiator, and some dissolved oxygen. Always there is some kind of oxygen present in any of the liquid. And oxygen is very reactive. So whenever the light falls, the oxygen goes first and absorbs that. And then photoinitiator is slow to move. So what happens is, look at this animation clearly. So oxygen goes first and then photoinitiator. When photoinitiator goes, then photo cross-linking happen and then you get voxel. That voxel is having the refractive index gradient because your beam is having Gaussian intensity profile. It acts as a lens. So what happens? Now for forthcoming light, this voxel form acts as a lens. And lens-like effect you get because of that. Yes. And this voxel is like this. Okay. And then, as I told, beyond certain energy, no more cure depth and saturation really happens. This is typical the reactions. So first is oxidation and then photopolymerization. And your species are continuously coming, your photoinitiator species. And that is given by this diffusion equation, okay, or mass transport equation. Diffusion and consumption terms. Negative is the consumption term basically. And then under such circumstances, your light is getting propagated in the Z direction. This can be typically modeled by Maxwell's theory of electromagnetic, like because light and your electromagnetic go hand in hand. So in Maxwell's theory E is electric field, and the light intensity of light is square of electric field. And the theory of electromagnetism can be applied to the light propagation and magnetic propagation. Is light propagation a similar theory. So based on the Maxwell's theory, then we can build on the nonlinear Schrodinger equation. And if you look at this nonlinear Schrodinger equation, it has different components like propagation of light in space. Then this negative part is propagation of light in absorbing media. This one, and this is in, you have refractive index gradient, so refractive media, graded refractive index media. And this refractive index is keep on changing. So you have to model this delta n, and this for this Villafranca model is being used, and along with this propagation, you are having diffusion of spaces continuously taking place. All this is taken care, and then modeling is being developed, and then a lot of simulation work is being done to observe and accurately observe this particular process. And then experimental work and then simulation work based on this mathematical modeling is being compared with each other, and the simulation is being validated. And then a lot of the understanding is being developed. And then based on all this experimentation, the process plan is being planned for the bulk lithography. And what are the inputs that we need to give is 3D model and exposure time, AOM calibration model, because AOM data need to be, and AOM understanding characterization need to be provided. And based on this, there's so many processing being used by so many the charts and model which I have presented here. And then it gives finally to have determination of scan speed, and then pitch and AOM signal. And if it goes, then you will be able to develop the component. These are the successful components being developed, like CAD model translated into CAD model, actual model, and then the magnified inside picture of one of the part of the fabrication being done. This is at low energy level. At high energy level, as I mentioned, the free form surfaces at underneath is not uniform. So you get some rough surfaces, but rough surfaces are having some typical advantage in biomedical field, and we use it in some biomedical application, this particular kind of surfaces. You can see the cantilever beam and then Fresnel lenses and all. So this is exhaustively being done and being presented. As I mentioned, we started with the micro electromechanical systems being used in automobile, being used in development of many components in the mobile, medical kits, industrial application, so many. Just excuse me, I'll have some water. And to develop these components being used in different applications, there are different processes. LIGA, inkjet printing, LCVD, low chemical vapor deposition, I mean to say. Two photon polymerization, EDM, laser machining, and so many. Where BL stands, okay, bulk lithography stands is mentioned here. This graph shows the feature size, complexity, and all those. So, this is the area. If your component is within this area, if you want to fabricate, sorry, then bulk lithography is good to go. Okay. You have all other processes also. You have to find out where and which process to be used. So at the end, I'd like to thank to my supervisor, Professor Prasanna Gandhi, to my co-supervisor, Professor T. Kundu, and my senior Dr. Suhas Deshmukh, who also whose work actually I have presented, and many other students who worked along with me during the time and my laboratory. Suman Masuwala Advanced Microengineering Laboratory, who contributed for this intellect work which I have presented here. Thank you very much. I have shared my mobile number and email here on this slide, and participant can note it down. And if you have any query which cannot be handled in the discussion forum, so you can discuss with me over phone or email ID. So at the end, I thank the institute who given me opportunity to present in this ATAL program. Also thank the AICTE-ATAL initiative, really a great initiative. It's maybe a sixth or seventh year the AICT continuously supporting this initiative, and many or in lakhs of number, or maybe more than lakhs, but would have touched the crore people would have benefited because of this initiative of AICTE-ATAL, and many exchange and dissemination of knowledge has been taken place. So great initiative by the government and AICTE-ATAL program. And because of that scheme, we are fortunate that we are interacting on this particular forum. So really thank you, AICTE-ATAL. And thank you for the host institute. Thank you to the Dr. Pawar who contacted me and for this program, and I happily then taken this particular opportunity to disseminate this knowledge. I also thank Dr. Rane who also uh, contacted me and make all those online and reminder in place, everything, you know. So thanks all for all those kind of a thing. And now I open to the participant. If any questions, then really I'll be happy to take.
Hello. If any
Yes, sir.
questions from participant can ask.
Yes, please ask question if you have. You can type in a chat box also if you have any question. A few compliments I received there. Thank you for that.
Yes, sir.
Thank you,
Moving forward.
Mr.
Hello.
Datta. Then
Yes, sir. I am Dr. Pawar. It
uh,
is my privilege and honor to deliver the vote of thanks for today's sessions. I would like to begin by extending our sincere gratitude to our distinguished speaker, Dr. Kiran Bore sir, for gracing with us with his presence and for his truly insightful sessions on additive manufacturing. Thank you, sir, for that enlightening presentation. Your talk was not only comprehensive, but also incredible engaging, providing us with a deep understanding of fundamental principles and diverse applications of 3D printing. Sir, you have expertly navigated a complex topic from additive manufacturing to its transformative role in the field of aerospace, medicine, etc., leaving us with a clear vision of the future of manufacturing. Your passion and expertise on the subject were evident, and we are grateful for the time and effort you took to share your invaluable knowledge with us. I would also like to express our heartfelt thanks to you, sir, and also thank all the participants for their enthusiastic presence and active engagement. Once again, thank you, sir. Dr. Boy, sir, for an outstanding session. Thank you, sir.
thank you very much, sir. Thank you. So I'll take leave, sir.
Yes, sir. Yes, sir. Definitely.
Yeah.
Okay.
feedback link is pasted here and also send on your WhatsApp group